Okay, what's up YouTube? This is RJ the Computer Doctor back with another video. And in this video, I'm going to be walking you through a machine learning problem. So if you are someone who is trying to get into tech, maybe you're trying to get into AI, maybe you're a computer science student who's trying to learn on like more machine learning fundamental problems. Maybe you're just a machine learning enthusiast and you want to know how a machine learning engineer would think through a problem, then this video is for you. Okay, so imagine that you have a client who comes to you with a machine learning problem. We want to build this model and trying to classify whether this person is sick or not. So here is the context of the problem. They collected some samples, and those samples consisted of 38 people who were positive, who had some kind of sickness. They had 83 people who were healthy individuals. So in data set two, just to make it a little bit more complex, they also collected samples from another population, which included 75 individuals who were not positive on the sickness that they were looking for, but they were sick, which had similar symptoms to the sickness they were trying to study, but it wasn't quite the sickness that they are looking for. Okay, and the basic thing that they wanted this model to output that you are trying to build is whether this person is sick or is not sick. So if you are someone in machine learning, maybe you went through a machine learning class, this kind of sounds familiar to a supervised machine learning problem. So in machine learning, you can classify most of the problems that you are trying to solve in as supervised learning and unsupervised learning. This is a traditional supervised learning problem because we do have labels. If we didn't have labels, then that's when you would try to do something like unsupervised learning, where you would try to do like clustering methods. Okay, so the main thing that we want to try and figure out is whether someone has a sickness or not. So a big thing before you get started with doing any feature engineering or trying to build the actual models is try to think about what kind of model that you're trying to build. Okay, so the first thing that you want to try and look at is the business goals. So what I mean by business goals is not actually doing business, it's actually getting to the root problem that you are trying to solve. So one way that you can approach this is combining these two negative samples and this noisy negative samples. So if we were to put these two together, we would get 83 plus 75, which includes negative, which is healthy and noisy samples. And then we would have our 38 positive samples here. Okay, so if you were to group these two together, you need to understand what you are trying to actually build a model of. So from this 75 noisy samples, these are people that look similar to the actual sickness that you're trying to study. So this could be a good start on trying to build a model to separate or to try and separate those two apart. But one thing that you need to keep track of is that if you were to include this 75 noisy samples, is that what you're teaching that model is to separate the sicknesses that were only included in this sample size. So this is a very low sample size. It's only 75 people who were sick. And there's probably only 4 to 5 sicknesses that were included in this sample. So in a hospital setting, if you are trying to build a model where people can come into the hospital and then they put their markers, their features into this model that can classify whether the sickness is actually true or not. If you were to include this 75 noisy samples, you are really only separating the kinds of sicknesses that were only included within this sample size. In reality, there's so many other sicknesses out there that might be similar to this sickness that you're actually trying to look at. So maybe including this into the actual data set may not be a good way to validate whether your model is actually doing its job or not. So another way of looking at it is to separate it this way. Okay. So another way of combining these three data sets is that you can actually train your model to pick up on those 83 healthy individuals and then test it on the 75 noisy samples that you included. So this would be together your training and validation set. And then you can keep this as a held out test set, which can help you figure out whether your model is able to generalize to a different population. So what I'm trying to say is that there's different ways you can try to combine this data set and input them into the model. And depending on how you try to combine these data sets together, it changes the whole way that the model is interpreting the data. This, I'm not saying that any of these ways of combining the data is wrong or is correct. You would need to double check with your boss or try to explain to the person who wants you to build this model that if you were to combine it or separate it in certain ways, that this would affect how the model learns. Okay, so name this combination 1 and combination 2. So each phase that we're trying to go through here, we are trying to look at the business goals to try and see if it matches the actual problem that we're trying to solve. So the next step of you have a data set of samples of people who have a sickness versus not have a sickness versus have some kind of sickness that's similar to the sickness that you're trying to study. The next thing that we can look at is what kind of features do we have. So features are basically anything that you can put into the model that the model can learn from. In sicknesses, the basic thing that you can look at is blood markers, which include like things like your white blood cells, red blood cells, hemoglobin, and all the other blood markers that you normally would typically get when you are trying to get a blood test. Internally, you might need to have some sort of sickness that's maybe rare or have some kind of cancer or a disease in order for the doctor who is trying to look at you to look at additional markers that might explain the sickness that you have. So then you can include it in a feature set of trying to figure out what kinds of features that you actually want to study. So there are methods that you can use in order to filter down the features that you collected in here. So the first step would probably be to look at what are all the features that you think matter in this scenario. And then you can use things like ANOVA, logistic regression, and looking at a kappa score, which are all different methods that you can use for feature selection. So if you just search on Google for feature selection methods, okay. If we look here, you can use things like Pearson correlations, chi-square tests, ANOVA, information game, mutual information. So these are all the different ways that you can statistically look at your data in order to filter down the features that you want to include in the model. The reason why you don't want to include all the features is that there are features that can hinder the model and degrade its performance. So you only want to really include features that have some sort of correlation between the thing that you are trying to model off after. Okay, so then we can boil it down to say these 8 features here. We have different blood markers, and then we have demographics, which include like age, ethnicity, gender. And then there's other things that you can do to improve or to increase the number of features that you have. So this is through a process called feature engineering. And in here, you can do things like analysis. You can include ratios. So if you were to take the ratio of white blood cells and this PTX3 and just include that as another value or include that as another feature of your feature set, you can do that as well. You can include correlations between the data using Pearson's correlation. So there's other ways you can increase the number of features that your model is trying to learn from. So keep in mind, feature engineering is probably a more advanced method of trying to increase the number of features that you have. You could probably build a good model based on the features that you already have. I would only go towards feature engineering if you are trying to build a model that's going to be as precise as possible. And if you have more time, and of course, if it's a very risky scenario where you need to have like over 99% accuracy, then you can go towards this feature engineering route. Okay, so that connects back to the business goals. So are these the features? Since you have these features, the next question you have to ask is whether these features are always going to be collected during the time that you are trying to use this model during inference. So things like these blood markers are these aren't typical blood markers that you would study during a typical exam. they probably have to draw more blood from you, or they have to just check, the doctor needs to check it off on their list for things that they need to check your blood for. And a lot of these tests do cost the hospital money in order for them to look at your blood. It's additional time. So if these blood markers aren't able to be collected during the time that this model is actually going to be used, then you can't include those blood markers. And if you can't always get the demographics like age or ethnicity, if that's an issue, then you would probably be better off excluding those from your feature set. So that's just connecting it back to the business goals. Okay, so another thing you can look at is cleaning your data. So a lot of the times, if you're trying to look at real data from some sort of source, then there's probably going to have empty values somewhere in there. And it's up to you or your boss to look at the decisions of whether to remove those values, or you can impute those values. So impute is basically statistical methods where you can replace those empty values with values from the data that you do have. So another term that you can use here is bootstrapping, or you can use the median, or you can use an average of what data that you already have. Just understand that if you were to include these values, that they may not be representative of the actual data that you are getting. So just understand that if you are to use these imputing methods, then they may not represent the actual population that you're trying to use this model in. Okay, so the next big thing that we are looking at is how to split up your data. So since, as you've seen, this data set is pretty small. So we do have 83 plus 38, 121. So if we were to go with combination one, we have 121 samples overall, and we have 31% of them as positive and 69% of them are negative. So there's methods that you can use in order to kind of increase the number of data points that you have within your data set. So SMOTE is synthetic minority oversampling technique, which is basically grabbing the data points that you do have. So picture this here, where we have this cat would probably represent data points that you do have, and then these placeholders between those real data points are synthetic data points that you would create. So how SMOTE works is that you would grab a real data point, and then you would basically draw a line between the other data points that you do have, and then just fill them in with random data sampling. So then your data is just basically using a cluster of the data that you already have. And then there's other methods here. I guess it's borderline and density, which it looks like if you want to include data points from only a certain number of data points that you do have, or if you want to cluster the minority data points around some sort of data point that you already have. Okay, so another method that you can use if you don't have a lot of data points is you can use stratified crossfold validation, which is basically you would build 5 or 10, typically 5 or 10 is chosen for the number of folds that you have. And then you would build these 5 or 10 different models based on a similar ratio that you had in your data set. So if you had 31% as positive and 69% as negative, then you would keep that ratio of 31% positive, 69% negative, and you would also separate out a test set. There's usually a test set where you need to use in order to test the model that you are trying to build a model off of. And so what you're doing here with is stratified crossfold validation is that you are reducing the bias that you would get from building a single model that might be looking at a heavily influenced data points that you have within your data. So if I were to draw, can I draw something on here? So if you were to draw what your data set might look like, your data set, it might have, this is a, so picture this, oops. So picture this as a graph. So what your data points might look like is, say that you don't have a good distribution. Maybe you have data points there, maybe it goes up, down, and it goes up. And then we have this high ceiling here for what the data looks like, and then it goes back down. And if you were to build a single model based off of this data, it might be looking at a large proportion of the modeling might be looking at this portion here where the data set is heavily influenced, it's heavily biased in a certain area. But if you were to build 5 different models off of it, it smooths off the distribution of what the other models is trying to learn. So by doing it this way, you get a larger, it increases the probability that you can build a model that looks at the entire data set rather than only focusing on this single part here. And then there's always some pre-processing that you need to do on the data. So once you have your data split, you have a way that you're trying to build the models off of, you have all of your features, then we need to go through the pre-processing step, where this is where we actually turn those values into a way that makes it easier for the model to learn. So in standardization, or you could use normalization methods, this is basically turning your data, compressing your data into a format which is easier for the AI or the model to learn from. So this is used a lot in neural networks because if you were to use very large values in your input feature set, at a point when you are trying to train your model, if you have multiple layers on there, then those through the way that the model learns, from my understanding, is that those values that you have, if those values that you have for your feature set, they can exponentially grow as they progress throughout the layers of learning. So in tree-based methods, you're basically just trying to find places in the data where it is optimal to split off to find the differences in values that make the most sense to create the split that you are trying to look for. And I kept a note here that this is only done on the training data. Standardization is you're doing it on the data set that you have. The reason why I put this on training data is because if you were to include the test set, so I have a test set, held out test set that I excluded from this training portion, which is supposed to be representative of data that the model hasn't looked at before. If you were to include that in a data set, then you are only really standardizing the data towards the actual samples that you do have. But if you were to standardize data that you were to receive from a different population, then it's not going to map one-to-one with the standardization that you already pre-process the model from. Okay, so another thing is one-hot encoding, which is just basically turning qualitative data into numerical representations. So if you have gender here, which you have male and female, this is basically just turning that data into 0 and 1. Even same goes with ethnicity. You are trying to change the qualitative data that you do have, which are not representative numbers, and you are mapping them to a number that makes sense to the model. Okay. So once we have finally a way to pre-process the data, then we can move on to collecting different metrics. And this metrics that you collect is heavily influenced by business goals that you do have. The basic metrics that you can measure is accuracy, and recall, precision, and F1. So accuracy is the basically the how much you got right versus how much you didn't. Recall is out of the number of times the model was guessing correctly, how much of those were actually correct. Precision is telling you the prediction that the model did have, how much you can trust the prediction that the model gave you. And F1 is some formula that combines the recall and precision. Other things like training loss and validation loss. So if you are using a neural network, there are several things that happen within losses. We see at a certain number of epochs, we have a validation loss that is separating from the training loss. So that means that the model that you're trying to build is not generalizing well with unseen data. So at that point, you might need to go back within this pipeline of figuring out whether to include different features, do more feature engineering, especially, yeah, it goes with the model that you chose and what hyperparameters you're choosing. So if we go to a different model here, we see that the training loss and the validation loss are decreasing together. But then there's a certain point where the validation loss is actually increasing. So at this point, at this number of epochs, this would be the best time to save the model's parameters and the model that you chose. And then this would be the one that you would choose to do the modeling or to do the modeling after. Okay, so next step is to choose the actual model that you are trying to solve for. In classification methods, in machine learning, you would typically start from the lowest complexity models. That's basically because these models are the highest in interpretability. So you can see what features you have is actually working or not. And they're usually pretty quick to learn, and you don't need a lot of training data in order to train these models. So logistic regression, random forests, and support vector machines are usually more higher in complexity. So the reason why you would want to use a non-complex model too is that they're typically faster in these situations. If you want to prioritize speed, then you would use these more simpler models. But if you have some features that are very complex and it's hard for these simpler models to learn from, then you can use these more advanced classification techniques, which is using a neural network or using transfer learning, which maybe people have built a model and then you can do some transfer learning to have the model fine tune on a data set that you have. Or you can use a large language model. And yeah. And of course, when you are choosing your modeling, you need to figure out what parameters you are trying to tune. And once you have some sort of parameters that show a high precision, recall, accuracy score, then you can use the final test set that you have to test the model. So this is, say you have your model here that was created. Okay, so out of all of this, all of these decisions, making sure they meet the business goals, and then you choose some parameters that are performing well on the validation set, then you can take the test set that you had, which was not included in any of the training or validation process, and then you would test it on this unseen data here. So this test set would be representative of the real data that's actually coming through your model. And you would have these several metrics that you are trying to optimize for. So if this model is producing a high accuracy, like 89%, and a high recall, high precision, then at this point you have a pretty good model that you can deploy. But and then there's also other different things that you need to watch out for, which is data drift, because since your model is performing good at one period, things change over time. There's probably different sicknesses that can mutate or have different markers as time goes on. So at that point, you would need to include that sample from the new data set, this training process, and you would have additional decisions that you need to look out for in order for you to make sure the model is performing correctly or not. Okay. All right. Thank you all for watching this video. That's all I have for today. If you did like this video, if you learned something, please give this video a like and hit subscribe, and I'll see you guys in the next video. Thank you.